Thank you for the kind introduction, and thank you all for joining today. Before I begin, I want to give a little bit of motivation and background for this webinar. When measuring easy samples such as polystyrene and water, you can pretty much put the sample in, hit run, and trust the result you get. But as you all know, real samples are very far from polystyrene. Your samples might have attractive fluoresces, they might fluoresce, they also might be formulated in a high salt buffer. All of these things can cause measurement artifacts. So the purpose of this presentation is to help you identify what sample properties can cause measurement artifacts, how to identify these artifacts, and finally, to provide you with the tools to overcome these challenges. Let us begin with dynamic light scattering, which I would now refer to as DLS. DLS is a technique used to measure particle size. Wyatt technology has three different detectors that can measure particle size. One is the Dynapro Plate Reader 3, which measures size and molar mass in a plate format. The Dynapro Nanostar measures size and molar mass in a quartz cuvette or a plastic disposable cuvette. And finally, the Mobius measures particle size and zeta potential in either a quartz cuvette or a peak flow cell. In this slide, we have the instrument setup for dynamic light scattering. To begin, the laser is cast upon the sample cell. The sample scatters a fraction of that light into an optical fiber, which then goes into an avalanche photodiode. This diode tracks the scattered light intensity as a function of time. This is then fed into a correlator board, which creates our correlation function. From the previous slide, you might be wondering what exactly is creating these fluctuations in light intensity. To understand this, we have to think about what exactly is happening inside the sample solution. So let's first imagine the figure on the left where we have time zero and we have two particles where the light is being scattered off these particles. In this case, the light scattered is in sync with each other. Therefore, the photodiode receives constructive interference and therefore a larger voltage signal. However, let's now imagine a little time later where these two particles have diffused a bit apart. Now, the scattered light is not in sync, it's a little bit out of sync with each other. Therefore, the diode receives a lower voltage because there's deconstructive interference occurring there. The main takeaway is that fluctuations in light intensity over time is due to Brownian motion of these particles. Now that we understand what causes these fluctuations in light intensity, I wanted to give two examples where these fluctuations in light intensities would be different. In the upper left figure, we have 4 nanometer particles in water. These particles are small, so they diffuse very quickly. As a result, we have fast fluctuations in the light intensity. This causes the correlation function to decay at a fast rate. In contrast, 40 nanometer particles in water diffuse very slowly. As a result, the fluctuation in light intensities happens at a slower rate. As a consequence, the correlation function decays at a slower rate as you see in the bottom right figure. So far, all of the solutions we have described are very simple in that all of the particle sizes are the same in solution. But real samples often have aggregates, and also they might have multiple populations of particles in solution. So a common question that arises is, what model do I use to determine my particle size? Let us begin first with the simple example. In the first figure, we see that all the particle sizes are the same, and to describe the solution, we would say that it's a monomodal and monodisperse. And in this correlation function, it would have a single exponential decay. And the model that we could use for it is called the cumulance, because the cumulance model only uses a single exponential decay. Now let's move to a sample that's a little bit more complex. In this second figure, we have a solution that's beginning to form dimers and oligomers. In this example, we would still describe it as monomono, but we would also now say that it's polydispersed because there's a little bit of variability in diameter, and we could see that from the histogram. In this example, it is still appropriate to use the cumulant model. Next, let's consider an example where we have two different populations that are very different in size. In this case, we would call it multimodal. But the samples themselves, each population, will be considered monodispersed. But because there are two different populations, what happens with the correlation function is that we see two decay times, one for the smaller species and a second for the larger species. In this case, it is not appropriate to use the cumulant model. Instead, we need the regularization model because the regularization model actually fits to multiple exponentials. And that allows us to create this histogram where we see two different species. Finally, let's move to an even more complex solution where we do have two different distinct species, and those two species have polydispersity within them. In this case, the solution would be described as multimodal and polydispersed. And in this case, we would also be using the regularization model. Thus far, all of the autocorrelation functions I've shown have intensity that decays down to 1 over the collection interval. However, there are situations where you might see a foot in your autocorrelation before it decays down to 1. This is actually called number fluctuations. If you work with large particles, say above 100 nanometers, this is most likely due to the concentration being a little bit too low. One solution is to just simply increase the concentration. But if you work with small protein particles, this is most likely due to some aggregates or dust in the solution that basically flow in and out of the beam path during the collection interval. One way you could remove these foots is to physically filter the buffer and sample. You could also centrifuge the sample and only take the supernatant. Lastly, you could reduce the appearance of this foot by reducing the acquisition time to 1 second, which is usually typically 5 to 10 seconds. You could also apply baseline filters, such as the 0.01 baseline filter. This will essentially remove any acquisitions that show this foot. And lastly, because some data might be removed, you might want to increase the number of acquisitions you take of this sample. In the previous slide, we discussed how having a concentration that is too low can cause some artifacts. However, if the concentration is too high, we could also have another effect called multiple scattering. As an example, let's consider we had a solution that's 100 nanometer particles at a pretty high concentration where the solution is opaque. Let's call that zero dilution. In this case, if we tried to measure the particle size, we would get an underestimation, say 85 nanometers. But if we begin to dilute the solution, we would get closer to the actual size of 100 nanometers. To understand what is happening in this high concentration regime, we could look at the figure in the upper right. In this example, the light is scattered off the first particle, and ideally, that scattered light would go straight to the detector. However, at higher concentrations, we might have multiple scattering. The effect is that the correlation function will decay at a faster rate. This would cause an underestimation of the particle size. A simple solution is to keep diluting the sample till the solution is clear. In addition, the most accurate way to measure a particle size is actually to prepare the solution at a couple different concentrations and extrapolate to zero concentration. This is also useful when you have samples that have high attractive or repulsive interactions. Thus far, we have discussed how particle concentration can impact the measured radius. However, the solvent itself can also influence the measured radius if the solvent changes in viscosity. As an example, let's imagine that we had 200 nanometer particles in water, such as shown in panel A. Now let's imagine that we begin to increase the viscosity of the solution by gradually adding in more glycerol. What happens in solution that these particles begin to diffuse at a slower rate, and the software, if it's not correcting for this change in viscosity, will think that the particles are actually larger than they really are and overestimate the particle size. To correct for this, the Mobius software has a database of a number of different solvents, such as glycerol 10% or 20%, and also the corresponding viscosity. By plugging this correct viscosity into the Stokes-Einstein relation, we could extrapolate the correct radius of the particles. In addition, the Mobius software also has built-in methods that will allow you to calculate the viscosity of your unique solution by simply spiking your solution with a known standard and comparing that size change versus that standard in pure water. Another sample property that can cause complications to dynamic light scattering is fluorescence. So far, the assumption has been that all the light being received by the detectors is that of scattered light. But if there is a little bit of fluorescence in the background, that can completely wash out the correlation function. As an example, I have these three figures presented here. On the leftmost figure, we have the correlation function of a protein without any fluorescence tag. If we now modify that protein with a weakly fluorescing tag, then what we get is the middle panel, where the correlation function appears a bit noisier. However, in most cases, any modification in any fluorescence in the sample will completely wash out the correlation function, as you see on the rightmost figure. This might actually make a user think that the sample is a solvent-only sample and there are no particles in the solution. But the difference between a fluorescent sample and that of a solvent-only sample is that the fluorescent sample will have an intensity in the million counts per second, versus a solvent-only sample will have an intensity with 100,000 counts per second. In regards to solutions to overcome fluorescence, one nice feature about the Mobius is that it can be configured to add a bandpass interference filter. This will basically filter out the majority of the fluorescence. In addition, a different solution is to simply use a wavelength at which the sample does not absorb and fluoresce at. So instead of using the 532 nanometer laser of the Mobius, you could measure the particle size with the Plate Reader 3 that has a 830 nanometer laser. One of the nice features about the Mobius software is that you can measure the size with a third-party software or instrument, and then plug in that radius into the Mobius software. The Mobius software will then use that radius and the measured mobility to calculate the zeta potential. Thus far, we have discussed some of the challenges that can arise when measuring dynamic light scattering and how the Mobius can provide some solutions for those challenges. I would like to now transition into the measurement of phase analysis light scattering, or PALS. In this slide, we have the instrument configuration for phase analysis light scattering. The Mobius unit uses a high-power 50 milliwatt 532 nanometer laser wavelength to cast upon the sample cell. The scattered light is collected by 31 independent diodes. In the sample cell, we have the two platinum electrodes, and let's just assume that the bottom platinum electrode is polarized negative. Let's also assume that the particles in solution have a net positive charge. In this case, the particles will move in the downwards direction. As a consequence of this movement, the wavelength of light received by the upper half diodes will be redshifted. However, the wavelength received by the bottom half detectors would be slightly blue shifted. This shift is proportional to the net surface charge and the total charge of the particle. However, this shift is very difficult to detect. It's very small. So a method that is used to detect this small change is called interferometry. In this case, we take a small fraction of the original laser light and recombine it with the scattered light. This creates a beat pattern. The frequency of this beat pattern is then used to calculate the mobility. But mobility alone isn't sufficient to calculate the zeta potential. You can see in this equation on the right, an accurate calculation of zeta potential requires knowledge of not only the mobility, but also the particle size. For that reason, there is a built-in dynamic light scattering detector in the Mobius unit. This allows us to measure mobility and particle size in the same scattering volume, so there is no need to switch any cell or remeasure the sample. As I will cover in later slides, the accurate measurement of zeta potential requires simultaneous DLS and PALS measurements in the same sample cell. Now that you have a better understanding of how phase analysis light scattering is measured, I wanted to give you an example of typical PALS data. Here we have what's called a V-graph. On the y-axis, we have electrophoresis per unit electrical field, or you could think about this as the distance moved per electrical field applied. On the x-axis, we have time. If we divide the y-axis by the x-axis, we get this blue line we see here. The slope of this blue line is actually the units of mobility. If we were to increase the surface charge of our particles, the slope of this line and also the mobility would increase. Another useful aspect of this figure is that the direction of the V-graph tells us about the net surface charge. If the V-graph points in the downwards direction, as shown here, we know that the net surface charge is negative. However, if this V-graph points in the upwards direction, we would know that our net surface charge is positive. In this figure, you also see some green triangles. These are for the right axis, which is the current. This is basically to show that the current is being tracked as the voltage is being applied. A sample property that can cause complications to the measurement of zeta potential is if the buffer is conductive. Even just 10 millimolar of salt can cause complications. One complication is the formation of bubbles from electrolysis. This would basically impact the field being applied and therefore lead to an incorrect mobility value. A second complication due to high salt is dielectrical shielding by the ions themselves. The effect of this is that the particles of interest will feel less the field and therefore move less, leading to an underestimation of the mobility. In regards to solutions, bubbles can be overcome by using the Atlas accessory, which can pressurize the flow cell with 500 psi. In regards to the challenge of dielectrical shielding, what can be done is to switch to a higher field frequency. So instead of using 10 Hz, we could use 20 Hz. An example of this can be seen in the bottom two left figures. On the bottom left figure, we have a measurement in high salt with 10 Hz frequency. We can see that the V curve is dominated by noise, and also the slope is very shallow. However, if we switch to a higher field frequency for the same exact sample, we recover the V curve, we get a better fit and a larger slope. On this bottom right panel, we see that the software allows the user to select which field frequency is to be used. In the previous slide, we showed that the presence of salt ions can cause complications such as the formation of bubbles or dielectrical shielding. Another thing that salt ions can do is change the model that should be used to calculate zeta potential. For example, the Huckel model should be used when you have samples of small particles in a low salt solution. In this case, the F function approaches 1. This value will be plugged into the upper right equation to calculate zeta potential. However, the Shimokowski model should be used when you have large particles in a high salt solution. In this case, the F function approaches 1.5. What you could see is that the total range of the F function is between 1 or 1.5.
What this means is that the error in the zeta potential can be as high as 50% if you were to select the wrong model. In actual samples, you might not be at one of these extremes. For example, if you had a protein solution, which is small particles, it's unlikely that you would formulate them in just water. You'd probably have some salt ions present. In this case, your value wouldn't be directly 1, it might be 1.2. For this reason, the Mobius instrument has a third model called the Henry model. In this model, we are able to plug in the ionic strength of our buffer. The software will then calculate the exact F function that should be used to calculate the zeta potential. If you do not know the ionic strength, there is also a built-in calculator where you could list what ions are present in your buffer at what concentrations, and the software will calculate the ionic strength. In the previous slide, we showed that knowledge of the particle size and ionic strength is necessary to accurately calculate the zeta potential. However, there are times when the particles are too big to be measured by dynamic light scattering. In the Mobius instrument, the particle size can be measured up to 5 microns in radius. But when the particle size exceeds this limit, an alternative technique can be used, such as scanning electron microscope, tunneling electron microscope, or atomic force microscope to measure the particle size. This particle size can then be inputted into the software, which will use that radius to calculate the accurate zeta potential. For those who measure particle size and zeta potential, they're often interested in also the stability of their particles. One way to further study stability is to measure your particle size and zeta potential as the temperature is being ramped, or to hold the sample cell at a fixed temperature over a set amount of time. You could see from the equation on the bottom that in order to accurately calculate zeta potential, you need to know both the mobility and the radius simultaneously. This can be complicated because the size might be constantly changing as the temperature is being ramped. As an example, let's take a look at the figure in the upper right. On the y-axis, we have the temperature, and on the x-axis, we have time. At time 0, we have the sample cell at 25 degrees. We then ramp it up to 60 C, hold it there for a few hours, and then cool it back down to 25 C and hold it there for a few more hours. During this ramping, we are measuring the particle size, which we see that begins to decrease in size at first, slightly increase as the temperature is being held, and interestingly, significantly aggregates and forms large particles once the samples cool down. In the Mobius instrument, we simultaneously measure dynamic light scattering and PALS. This allows us to simultaneously measure the mobility of the sample and therefore calculate the accurate zeta potential across the whole temperature ramping profile. The Mobius instrument has two different types of cells that can simultaneously measure DLS and PALS. One is the Mobius dip cell, and the second is the flow cell.
To conclude this webinar, I want to give a few tips on the method development for delicate samples. Some samples will begin to aggregate and increase in size when a voltage is applied. For these samples, what I recommend is to first inject the sample and then measure at different voltages from 0 to, let's say, 5 or 6 volts. And at each of these voltage ranges, you want to measure the sample 5 times very quickly. For example, the DLS would be very short with 1 second acquisitions, and you do that 5 times. And the PALS collection would be a total duration of 5 seconds. So both DLS and PALS are only 5 seconds. And we do this 5 times to see the reproducibility at each of those voltages. And what you see on the right side is we have the figure of the result. So for the radius, we see that the radius was actually quite constant throughout all the voltages used. So this is a good thing. We know that the sample is stable. Next, we want to look at the zeta potential as a function of voltage amplitude. And we can see that it takes till about 3 volts where it begins to kind of stabilize. So from this result, I would conclude that 3 volts is the ideal voltage that we would want to apply for this sample. Next, you could re-inject the sample and measure directly right at that voltage to get the accurate zeta potential without being compromised by previous measurements. And finally, step 5, which is optional, at that voltage that you found, in this case 3 volts, you could further optimize the settings by changing the collection time. Earlier, we were just using 5 seconds, but you could also collect at 10 seconds, 30 seconds, and 60 seconds to see if that brings the 5 measurements closer together.
To summarize, in today's talk, we covered a number of sample properties that can cause challenges when measuring dynamic light scattering and also phase analysis light scattering. We also discussed certain software and hardware features of the Mobius instrument that can be used to overcome these challenges. Thank you very much for joining the webinar today, and I'm happy to stick around to answer any questions you might have.